All right, so hey everybody. So I hope you had a good week. This week we do begin actually diving into a little bit more StyleGAN stuff, so not purely about data sets, so we'll have a little bit of fun with things. Just another note, we will be looking at some code today again, so if code is not your thing, what I recommend doing is all this stuff is already available within the scripts, the Python scripts. And I'm gonna make a note to myself to add the link for my like StyleGAN sort of like massive collab notebook, um, so that people have access to it. So I think like what's helpful about today is like we'll look at some code. You don't actually need to like understand what any of the code means, but I think what's helpful is like we're gonna actually look at what a vector looks like, as well as some other features. So I think the idea here is just like think about these as like instead of looking at them as a long string of numbers, like reduce them down to like one or two numbers, and then like think about how the math works on that. And I think that'll sort of help everyone sort of like wrap their head around what we're doing. And then, we will also like all this stuff is available via the scripts that I'll include in this collab notebook. Um, so we'll still be able to play with a lot of these things and still be able to access them. So I find this is like a nice mix of like stuff for different folks, and hopefully you'll be able to like just sort of like even if you can't immediately get it, like maybe watch the video again later this week and see if you can soak up a little bit more of it. And regardless, I think there's stuff to play with and at least see um, on that end. John's asking if anyone else has a choppy connection. No. Okay. Sorry, it's about you. Um, yeah, so I will add that notebook to our slides or to our class list. So the other thing I wanted to mention was I added some new stuff to StyleGAN this week. I took some things from there's a artist and technologist by the name of Vadim Epstein, and he has a bunch of other cool notebooks, which let me link to his work. And he had a really nice script to generate non-square outputs from our square models. So I've included that in the newest version of my like repo. I'm finding that certain things break with that, with those changes. So if you come across something that breaks, especially if you see something that says init_res, if you come into an issue with that, just like DM me and I can maybe like debug it really quickly. But I'm also planning to record a video probably this weekend or tonight about how to actually use that. So if you are interested in playing with that more, that'll be available very soon. I can just really quickly show what that looks like. So basically what this allows you to do is it allows you to take our square model and not even really stretch it. We're sort of like doing this other technique, which maybe I'll get into maybe in a couple other classes, as this kind of relates to how network bending works. But essentially, it allows you to sort of like take your square and sort of add to the ends of it, and through a little bit of like adding a little bit of noise, it's able to sort of like generate stuff that looks pretty realistically rectangular. So I know everyone's like, how do I make 16 by 9 videos or that sort of thing? So this new tool will kind of give you something close to that. It's probably better for abstract stuff than it is for like faces, because you'll get weird half faces on other ends. Maybe that's cool too. But it's worth playing with and just sort of seeing what you can get. So I'll record a video this weekend about how this works. There's a couple other things you can play with, but that should be a cool, fun thing to play with as we begin to like get through more of this stuff. Let's see. Dust, do you want to talk a little about the tool you're making? Because it looked pretty cool.
Yeah, sure. I don't know. I was like, oh, I don't know. It was kind of inspired by like, when you fire up a StyleGAN in Runway, it has like this grid of like images that are all the different vectors. So I was like thinking like, how would you explore like a space of like editing images and like scoring them against LPIPs. So yeah, I don't know. It's basically like you load in a data set and a couple images to run against it, and then yeah, I don't know. It kind of um, my transformation, I only have one right now, isn't really working quite right. But I don't know, the basic idea is that like you can have two transformations going at a time, one in each axis, and then whatnot. So I don't know, it's definitely still really kind of needs a lot of work, but it's interesting, I feel like. So yeah.
Cool. Yeah, I think it's an interesting tool, and it's like sort of what we talked about last week, which is like what happens when you actually change some of these images and move things in certain directions or scale them up and scale them down. Like, how does it actually affect LPIPs? Which I think is a really nice. It's starting to like really nicely visualize like how the model actually sees things. So I think once a little bit further along, it'd be cool to. Again, I'm happy to like help record a video or something to talk about how you could use it. Or I guess right now you sort of need to do it locally, but I'd be interested to see if maybe there's a way to turn this even into like a collab notebook where you could quickly spit these out and give scores. So I think there's lots of cool opportunities with this. Yeah.
Yeah, I don't know. Right now, even with, well, I don't have a great GPU on my laptop, but it's like better than nothing. Even then, it like takes like 20 seconds or so to run LPIPs. So it's kind of, that's why I don't know. It's still not great user interface. So yeah.
Yeah, I think that's just true of most GPU tools. Like, we won't look at it today, but maybe we'll look at it next week. But there's a new tool that allows like some feature vector things inside of Colab, and even then it's slow too. It's a challenge with when you're doing these when it takes a little bit more than like half a second to generate these images. It's a challenge, but I think it's really cool and really interesting sort of direction on things just to try stuff. So I know Grant also added he added an interactive tool. Grant, did you post that somewhere?
To the Slack, I don't think. Did I? I don't think.
Cool. Well, I'll mention it. I'll add it to the data sets, or if you want to add it to data sets. But he had a nice little tool that allows you in that interactive mode that we looked at in week one. I guess what is it? Y and N. You can like quickly just sort like so. It's like sort of like an interactive like yes, keep this image, delete, remove this image. So that might be fun for people to use instead of having to go through like an endless list of images in a folder. So yeah, might be fun to check that out.
Yeah, just put dash dash choose as your parameter at the end of the interactive script. It's documented in the if you run the help prompt, and it's in the latest. You've merged it into main, so you grab it off of your GitHub. It's there now, so you check it out. It should be pretty straightforward. Y and N are those magic keys, and yeah. When I do use your tool, I get this weird window that shows up that initially distorts the image, and then I have to close it before I get into the real processing change. So is that something that you see too?
I don't think I have before, but it wouldn't surprise me. I think there, OpenCV as a GUI tool is, kind of similar to how these other tools work. Not the cleanest. So,
Well, it must be a platform dependent glitch, but
yeah.
yeah, I was hesitant to try and tackle it because I don't want to break it if it's not. I don't want to break the functionality that's working fine for everyone else. So we can talk about that later or something.
Yeah, cool. And let's see, I think Nowco, you posted some stuff as well. Which let me go back to that channel and we can take a look at some of it. Do you want to talk about what you were working on?
Sure. So for work, I actually had to throw together a StyleGAN model last week at the very last minute, which, as you know, is kind of a challenge when you only have so many days to train. So, it's definitely undertrained, but they were happy with this. So I was like, okay, I guess that's fine for them. What I've noticed though, so essentially what I had to do was to remake the like the Google Earth one that's in Runway, or something similar to it, because it's a project on climate change. So you can't use that one because Google Earth is for non-commercial uses only. So what I essentially did was just go through Flickr and scrape NASA's like albums, because they're surprisingly, you can actually use those for commercial work. And there are a couple other public ones. So what I've noticed though is maybe around day 2 or 3, there was some definite structural mode collapse happening. And I know from the previous StyleGAN ADA class, that I remember it was brought up and it was like, well, just let it train for longer. And I trained it for maybe 2 or 3 extra days, and it just didn't really improve. So I'm not quite sure what's going on, and so I decided to run it through CLIP to see if it was, maybe it had just too many images of clouds or whatever, which actually was an interesting experiment just to do, because if I were to say train this again on what's it called, class labels, then it's maybe I have enough to do different kind of labels and maybe it'll generate better image, better results. I'm not sure. That's something that I have to do to apply.
Yeah, another thing I might recommend is, I don't know what you set the gamma to, but you might want to increase the gamma. I find that gamma tends to help control, if you have sort of a pretty disparate data set, gamma can help control that. You do lose a little bit of diversity, but it can sometimes help. And yeah, I think the mode collapse or just sort of having structural, sort of that understructure, is a big challenge. What did you transfer off of? Do you know?
FFHQ.
You might try transferring off of WikiArt. One of the nice things about WikiArt is because WikiArt is already pretty diverse. What I tend to find, especially with the PyTorch ADA model, is that when you transfer off FFHQ, it tends to keep that base structure really early on, like the face structures, just because of how it trains. Actually, Vadim and I were just discussing this and trying to figure out how to resolve this. He has some ideas he's going to try, and I have some ideas I'm going to try. But I think training off of WikiArt, because it's so diverse underneath, you might get better earlier results because of that. So that's something you can try. I mean, at this point, I'm personally training most of my models for 2 to 3 weeks on a single GPU that's actually a little bit bigger than the collab GPUs. It's usually on a 24 gigabyte GPU. And that's really what I found works best. It's just it takes long to train these things sometimes. So, it's hard to tell clients that. It's wait 3 weeks and we'll have a good model. But I think that that's one solution I found, but it's hard, especially on collab where you have to restart it all the time. It can be really annoying. But yeah, I mean, this is I think everyone is trying to solve some of this stuff, especially with StyleGAN, and it is a challenge.
Yeah, so when you say set the gamma high, it was at 50 first, and then I think because I realized that it wasn't improving, I set it to 100, but it also didn't really change anything.
Yeah, it's a bit of a fine art. Usually what I will do in most cases, I'll set mine pretty high. I'll set it 100 or 50. And then once I feel like it's gotten to be to a good place, I'll actually lower that and then keep training it. Because the idea there is that gamma sort of helps it stabilize, helps the model stabilize so you don't get these collapses. But once it's trained pretty well, you could actually lower it a little bit, and that would actually help diversify it. So again, easy to do over 3 weeks, a month, but a challenge to do over a week of time. So yeah. Cool. So hopefully, again, please feel free to share in the Slack channel whenever you want. And we'll tend to take the first 10, 15 minutes of every class just to sort of go over some stuff, because I think it's interesting to see what everyone's up to. All right, so with that, we can jump into today's lesson. All right, so as I mentioned, this week, we're going to start actually looking into StyleGAN a little bit more. We will today be looking at latent spaces and feature vectors. I know most of us probably know a little bit about how latent spaces work, but I think it's kind of good to actually dig into it, because especially as we get to later weeks, we'll actually be seeing how these things get manipulated more. So it's helpful to sort of understand what we're actually looking at when it gets manipulated. And then feature vectors, I think I've covered them before in previous classes, but it's always sort of a moving target about how to find the best feature vectors. And there's a newish technique that I'm currently using that we'll look at. And again, we'll look at some of the math underneath it so we can actually sort of see these things get manipulated. So we'll do that today. And just as a reminder, we do have co-working sessions Saturdays and Mondays. Saturdays, I probably will be 5-ish minutes late just because I do finish up a class right before that. And I will try to make sure I get the links right this time. I think on Monday I had the wrong link, so I'll update that in our calendar for everybody. And then, yeah, again, like if you can make it or have questions, please feel free. If you don't, no worries. They're just here in case people want to chat more or have an idea for a project and are looking for help for it. Okay, so let's dive into latent spaces. So some of this will probably be old hat for some of you, but I think once we get into the notebook, it'll be like interesting to sort of dig through. So by default, StyleGAN works with this thing called latent space. Right now, you're going to sort of imagine it as a 2D grid. In reality, it's like a really high dimensional grid, which is just kind of like beyond the human brain. But the simple idea here is that at each one of these points in space is essentially a representation of an image. And if we look at this image in this position, it looks like this face. And if we pick an image that is further away, we get a very different face. So the idea here is, positions essentially located in similar places have fairly similar features or fairly similar image representations. And the further away they are from each other, the more different they are. So again, if we look at an image that's really close by, you'll see that there's slightly different facial features, slightly different hair texture, like that sort of thing. So you can sort of see how these are represented. And so as I mentioned, the truth is like the way these are represented is by a 512 dimensional vector. It's really hard to conceptualize 512 dimensions. It just like doesn't work. Like even when we try to, we'll look at one of them directly in Colab, and even then it's just gonna be like, that's just a string of numbers. I don't know what any of it means. And the truth is, it is really hard. So what we'll usually do is we'll take a vector, we'll look at it, and we'll be like, that looks fine. And then we'll map it to an image and we'll just get an image out of it. And it's a little bit easier for us to understand what the image looks like compared to the vector itself. And I've talked about this briefly before in other classes, but StyleGAN actually has two different latent spaces. One is what they refer to as the Z space, and the other is what they refer to as the W space. And we'll look at some examples between those two. This image comes directly from the StyleGAN paper. I think the first StyleGAN paper, but don't quote me on that. It might be the second one. But the idea here, and this is what's really helpful to sort of visually represent here, is that let's say this is your data set. So for whatever reason, you've got a lot of yellow or blue or pink images, and you're sort of like missing a representation of something. This is all abstract. So like you could say like maybe these are animals, and you've got horses, zebras, and camels, but you're missing, I don't know, some rhinos or something. So the way the Z space works is the Z space is going to fill up the latent space as much as possible, which means there will be stretching to some of the representations, right? So it's going to try to evenly represent the data it has, but it's going to quote unquote fill the latent space. So no matter what you look for will be in the latent space. And that is different from, say, the W space. So the W space you'll see here is trying to more evenly represent the data. And it's trying to do it in a way that actually like is probably more coherent to how the data set was actually built. Now, the problem here is that let's say I want to move from this position to this position in the latent space. Well, here you'll see an issue where like there's no data, right? So the reason we use the Z space is that because it's filled, you can always move from one point to another. Whereas in the W space, it is more accurate to the data, but it's not perfectly representative of like any space in the W can be picked from. And this is a little confusing until we actually look at some examples of this, which is basically like what we will do is we will always pick a point in the Z space and map it to the W space. And then we'll be able to do interpolation in the W space because we know that this thing exists in the Z space and will therefore be mapped to the W. That might not make any sense just yet, but we'll talk about that a little bit more as we actually look at how to do this in code. But the reason that we actually care about the W space is twofold. So I probably showed this example in classes before, and you might have seen this. This is a linear interpolation in a Z space, right? So we are going from this dot in the latent space to this dot in the latent space. And as you move between that space, you'll see that this is probably not what you would expect for moving from this image to this image, right? So one thing you'll notice here is glasses pop up. The glasses pop up in here, and there's like, well, this person doesn't have any glasses, and this person doesn't have any glasses, so why are glasses appearing? You'll also notice that this person's mouth is closed, and this person's mouth is closed, but in the middle here, we've got mouth open and teeth showing. And this is what we refer to as entanglement. This is because this space is stretched. So as you go from here to here, you're kind of going through like a messy area that doesn't actually accurately represent the data. So that's where you get this thing called entanglement. So the W space, if we just take this and we map this Z image to the W space, and we match this Z image to the W space, and then we go smoothly through the W space, you'll see that we do not get teeth and we do not get glasses. And I would say even this image in the center here feels more accurately like what would happen if you were to add this person and this person together, right? I could say like the facial features, the hair color, just the middle part sticking around, like all of this is probably what we would refer to as like a better interpolation. And I like to think of these almost as like animations, right? If you were to do cell animation, and someone were to say like, I want you to just like draw me 5 steps between this to this, you probably wouldn't draw this person. So this is kind of how you can think about interpolation. So artistically, right, like maybe this is good because you get this sort of noisiness in your artistic interpolation. But maybe you just want a really clean interpolation, and this is the better way to get it. So the W space is usually your better option for interpolation. So let's quickly take any questions before we jump into the code about that. Okay, we'll take silence as no questions. So this is if you were to dig into the generate.py script, you would see much of this code already in there with maybe some minor modifications. So we can actually look at this really quickly. Let's just let me just run this real quick, and we can look at the generate.py script and talk about how to do this in that script, and then we'll look at the code that actually gets us there. So the first thing I'm just going to do is I'm going to actually install from the official NVIDIA Labs notebook, just because a lot of the code I have been adding recently has sort of made a mess of this. So I'm going to keep this a little bit cleaner and easier for us. I'm also going to download, I think this came from Justin Pinkney's awesome StyleGAN 2 model. I'm going to download a cat model. This is, I believe, 256 by 256, so it'll run a little bit faster for us as well. And if I come over here to my folder, you'll see that I have already downloaded the PyTorch model. And inside the generate script, you will see that so down here, we're going to start to import a bunch of libraries, and you'll see that those pretty much more or less match with what we have here. So let's do this real quick. Let's look at what it would be available, what we would do for the generate script to do this. So we'll do Python generate.py and -- help. And there's a couple examples here of what you can run, but you'll see that here are all of our options for, oh, interesting. Hold on one second. So this is, because this is the official repo, it doesn't have the same amount of edits as mine does. So let me add mine as well here really quickly. Let's do this. So let's go code cd .. and then we will download my version. Okay. Okay, so then if we do this script, sorry, all of my code has other stuff in it that we need to install. All right, so here we go. So inside of the mygenerate.py script, you will see there is an option here for space. And that space by default will be the Z space, but you could switch it to the W space. So in that case, what you could do here is you could say dash dash space equals Z or equals W. So those are options that you can switch between inside of my script. And then we'll look at here, there are also ways to generate seeds. So we'll look at seeds in a minute. But just know that all of this is sort of set up that you could do this directly from these scripts. What we'll be doing is we'll pull some of the code out of this, out of this library and actually stick it directly in Colab. So we'll take a look at that now. Okay, so first off, we're just going to install some libraries or like run some libraries in Python. I'm inside of the wrong folder again, so let me fix that. Okay, so we'll install a bunch of libraries. This will run very quickly. So the first thing we need to do is we actually need to install or like load that that model file, right? So we've got this model file here with all of our cats, and we need to actually load that into our system. So this line of code does this. I wouldn't worry too much about what this is. So the first thing we're doing here is we are just saying we will eventually be using a GPU. So this says to use a GPU. This now just literally loads our model file and all the weights inside of it, and it's going to push it to the GPU. So we'll run this line, and that's because I didn't specify this. So we're going to specify the path to this pickle file as a variable, and then we'll load that into our model. So this is pretty much, you will see this all over the place if you dig around in the code, which basically just says loading a pickle file. And then it loads g_emma basically loads just the generator weights. Okay, so we've got that loaded in our system into Python now. So let's take a look at how to actually generate a seed variable, right? So we see that StyleGAN uses what's called a seed. And a seed is literally a placeholder for one of our 512 dimensional vectors. So the way this works is we're going to use a library called NumPy. And all NumPy does is say like, hey, load this variable, this seed variable, into our random generator. And what happens here is that this way, every time we run this line of code, if the seed variable is the same, we're going to get out the exact same variable, or the exact same random numbers. And this is literally how StyleGAN uses seeds. So when you set seed equals 1, all it's saying is 1 is a placeholder for this 512 dimensional vector. If you switch it to 2, you'll get a different vector. But if you switch it back to 1, you'll always get the exact same vector between 1. If it's always set to 1, it'll always be the same. So this is just going to take our seed variable, and all we're going to do is we're going to produce a random number that is our 512 dimensions of a random number. So this g.z dimension is in some cases, some people can modify, you can modify your model to have as many dimensions as you want. By default, it's 512, and most people don't mess with that. So this g.zdem is just pulling from our model how many dimensions it has. It'll almost always be 512, but you might come across a weird model that someone has modified. So let's run this cell. Oh, and sorry, I should share this. So if people want to follow along, they can. It's also linked to from the deck. So we'll run this, and what we'll do is we'll actually print out what that 512 dimensional variable looks like. So you'll see here, we have 512 numbers, and these numbers run between negative 1.0 and 1.0. So every one of these numbers, if we were to count them, there would be 512 here. This is some mathematic notation where if you were to plug this into like Google, you would get out a like sort of like usually like a very small number, like a decimal number of some kind. So again, this is what our vector looks like. It's illegible. Like there's no way to really read this, but just know this is a placeholder for an image that we can generate. So if I switch this to say seed 21 and run this again, I think when I was here before it was like something like 8.8 something 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 E. So this is definitely different now. And if I do it again for 22, again I get a different number. But if I go back to 20, there's our little 8.8 E negative 1. So this is how seeds work. So anytime you specify a seed in your script, it is basically generating a 512 dimensional array just using the seed value. So that's pretty boring. There's not really like much you can do with those numbers, but we will be manipulating those numbers in future classes. And even I guess today in feature vectors, we'll be manipulating those numbers up and down. And how you change those numbers will affect your image. So you can't really read anything by looking at these numbers. Your eyes will kind of cross if you try to look at them too often. But just know that's where sort of all the power is in these models. So let's actually generate an image from that. So the first thing we'll do is, in order to generate an image, you need to push your vector to the GPU. So this line of code will just literally move this vector into PyTorch and then move it to the GPU. And now that we've got it loaded in the GPU, we can actually generate our image. So this is where you set the truncation value. You pretty much always want to set a truncation value. There is an option for none, which I don't really know what it does. Most people are just going to set a value, right? And so it can be really any number. Most people stick between -1 and 1.0. Noise mode, we don't really need to worry about this too much. Noise is sort of all the fine detail that is an image, and you can change it. If you're going to do interpolation, you pretty much want to keep it as constant, or you're going to have to like mess with that noise a lot, which we probably won't do in this class, but maybe we could do it toward the end of class, toward the end of the 7 weeks. And then we want to specify where we're going to save our image, and then this code will actually generate that folder. Because that folder doesn't exist, it's just going to fail, and you won't save out an image. So this line of code is just some Python that generates this folder. Because this is not a labeled or classed model classification, we just set our label equals to 0. If you were doing this model with like a bunch of classes, you would want to set exactly what class you're using. Let me know if anyone's interested in that. I can show you how to do that, but most of us work in unclassified models, so we'll probably just leave this as 0. Okay, so now this line of code, what this does is it's going to push our vector through the generator. This is what's called a forward pass. So we're going to take our vector and we're going to feed it through our model, and the model is going to return essentially like we'll actually look at this. It's going to return whatever 256 by 256 is. It's going to return that large of an array, and that stands for each pixel value. Actually, it'll probably be that plus RGB. So what it'll be like 256 times 256 to the third power. It'll be this many numbers, and this is our image. But what we'll find out is that this image is given a numerical value where every pixel has an RGB value, and those RGB values are between -1 and 1. And we don't really want that. That's kind of like, can't really do much with that. So this next line converts those values to a pixel value between 0 and 256. Actually, an RGBA value between 0 and 256. So for those of you that have done Photoshop before, you know that that's actually the range of an image an RGBA image that we use. Sonaka asked, yes, it does actually have a way to train class stuff, but I probably haven't done it before. So maybe that's something you and I can talk about, because there is a way to do it in PyTorch to do classes. It's a little different than the previous version, but I can probably figure out how to do that and send you some details on that. Okay, so this line will generate our values that are actually 256 to 250, 0 to 256. So this will be an actual image that we could, if you went through line by line, you could figure out what the pixel values are. One thing to note here is that if you've ever done stuff in OpenCV or pretty much any library that isn't like Photoshop, you'll find that often they swap around the values. So like I think OpenCV is BGR, so blue comes before red. So this permute actually swaps a bunch of them around. I could probably figure out exactly what it's doing here, but I think it might be BGRA. So there's lots of like little funky things where if you try to take this and convert this just to a 0 to 256, you'll run into issues with your color space. I pretty much find this and then I copy and paste it everywhere. I don't try to mess with this too much by hand, but this will generate this. So we can then look at this, and then finally we can take this value and convert it to an image that we can then save, and then we'll save it to this folder with this PNG. So this can look like a lot initially, but the truth is I understood what it meant, or like I figured out what it meant, and then I just copy and paste it everywhere. So if you don't know exactly what's going on here, but you are a little bit familiar with code, you can probably figure out how to copy and paste this into various places. So let's go ahead and run this cell and just see what we get out of it. And the first time you run this through a notebook, it just sort of, it's also like when our script runs, these two lines are installing some plugin code. And it's always slow the very first time you do this, but after we do this a couple more times, it'll be really fast. So we can take a look at what our code actually looks like. So this first image representation, when we did a forward pass through the generator, we got a bunch of pixel values that look like this. And you'll see that even Colab was sort of like, I'm not going to show you this whole thing. It truncates it because it doesn't want to display that much data. But you can kind of trust me that basically this is like an RGBA value between -1 and 1. So that's the first print here. Then we converted it to a value that is 250 or 0 to 256. So you could probably actually read these colors, right? So this is RGB, and this is an image. So like, this looks like a mid-gray, mid-gray, mid-gray. So that first colored pixels looks to be mid-gray. And finally, it saved out our image. So if we come over here to output and we double click on this, and sure enough, that sort of mid-gray color is that top left pixel. So again, there's nothing like really that spectacular to really look at here, but I just want to explain a little bit what's going on so that it's a little bit clearer about how you go from a vector to an image. This is the magic, right? This is where we actually take it and put it through the model. And that can be confusing, but just know that this is sort of where the magic happens, is here. So if anywhere you see a G, a capital G, that means the generator. So it's taking the vector and it's passing that through the generator. So that was a 15-minute lecture on how to generate an image, which probably takes 2 minutes through the actual notebook. But if you are interested in the code, there's you can like sort of start to play with this and understand a little bit more of it. So we made one image there, right? So like we generate one seed and we generate one image. We might want to look at how to actually interpolate between those. So let's look at how to do interpolation. So here we're going to define a function, and we're going to call this lerp. This stands for linear interpolation. What a lerp takes is it takes your endpoints. So you can think about that as that interpolation that I showed previously of the one person and the other person. So you take your endpoints and then you define how many steps between there you want to generate. So in that image I showed, there were actually 5 steps total, right? There was the one endpoint, then there were 3 midpoints, and then there was the other endpoint. What this code does, this is actually just like, this is a linear interpolation. There's nothing fancy here with machine learning. You can almost think about this as somewhere between like 0 and 1. So you can think about this as, let's say at one point you are at 0 and you want to get to 1.0. And if I were to say generate 3 steps between there, you know, you would sort of say like, okay, we'll divide this number by how many steps, and then add each of those to this. So it'd be 0.33, 0.66. Actually, I did that wrong, right? It'd be 0.25. It'd be 0.25, 0.5, and 0.75. That's essentially what this code does. It's fancier because we're doing that across multiple dimensions, right? So we're actually doing this across every single one of those 512 dimensions, which a human, it's going to take us probably an hour or 2 to do that. But for a computer, it takes seconds. Not even, it probably is less than a second to do that math. So this is used also for tweening. Like if you've done any animation using code, you will see this sort of something in this format everywhere, because this is also how you do tweening, or how you animate positions between one thing and do another, right? So you could think about this as a single 2-dimensional thing of X and Y. So if I want to go from 0, 0 to 1, 1, that's flipped for you, 1, 1. That's the math you would do to move it, right? So that's all this code does. So don't worry too much about exactly what this does. This is just a lerp function that you will find all over the place in mathematics. So we'll save this just so we've got defined. And then what we want to do is we want to take 2 z-vectors, right? So we're going to create a z-vector using a seed of 20, and we'll create another z-vector with a seed of 100. And remember, these seed vectors, I forget exactly what their max value is, but these seed values can be pretty high. So you could do 100,000 too. It's got something to do with floating point values. It's like something like 15,000 or something, whatever values total. So you've got some pretty high numbers. You can play with these numbers and get different things. So the next step is then we're going to call this function. And we're just going to say, hey, I've got these 2 points. So we'll say these 2 points. And then the number of frames I want between each of those is, let's say we want 72. So this is going to be, you know, I want 72 total frames between these 2 steps. And when I run this function, it will basically return all 72 points, or like all 72 512 dimensional vectors that we want. Then we're going to define, well, where should I put those images? And then we will actually run the exact same code. We'll modify it a little bit because we actually want to iterate over every one of these vectors, right? So we'll look at every single vector in these 72, and for each one of them we will generate image, and then we're going to save out that image. If you've never used enumerate in Python, this is really helpful, because what it does is it gives you both the z value itself as well as the index value in this array. Essentially, it's an array, or I guess it's probably a list in Python. They're the same thing, just depending on what language you use. So this will go through every one of those, and that's how we generate interpolation. It's literally, if we come back over here, it's literally doing a bunch of little steps as we get to here. So it's like, it's brute force essentially to generate our animation. Okay, so let's run this code. You'll see I'm doing some nice functions here of just printing out the values. So if this were like, let's say I did 7,200 steps, this would be a very, it wouldn't be actually that long. It would be a pretty long process, but not really that long. That generated in about 3 seconds, probably, give or take. So this just helps me know how far along I am. It's also helpful if you get an error or something, you can sort of figure out debugging it. And then if I come over here to my cell, or to my folder, in here I've got all my frames. So there are 72 frames. It starts at 0, so 72 total. And if I were to open one of these, every one of them, you know, just jumping around, you'll see I have a cat that is animating. So if I want to convert those into a video, the simplest way to do that is using an ffmpeg command. Again, you don't really need to worry about what this does. It just takes all those frames and turns it into a video. Let's run this really quickly. And that again took a couple seconds, and here's my video. So we'll download this really quickly. And there's my animating cat. Oh, that last part is pretty weird. So it looks pretty good for a while, and then we've got sort of a very gnarly looking cat there at the end. So that's just doing Z interpolation. So obviously there's a generate script that'll do that for you. But if you are interested in sort of the what's going on under the hood, that's what happens. Any questions? All right, we will move on to W. W space is fairly similar in terms of process. The difference is that we're going to take our Z vectors. So we're going to take these two poles here that we generated, and we're going to map those to our W space. So one of the important things I think is really kind of helps to remember is you pretty much are always generating a Z vector, and then you're taking that Z vector and projecting it to the W space, and then you do your interpolation in the W space. So a common thing that someone might think you should do is you generate all of your interpolations in the Z, and then you map every one of these to the W. And that's kind of silly because, again, remember that what the Z-dub does is when you map a Z to a W, there is always a position for it. So really all you're doing is you're remapping the image you've already got to the W space. So what you really want to do is you just want to map individual points, or like sort of your tween points, to the W space, and you want to interpolate in the W, because interpolating just by reproducing all your Z's will just give you back the exact same animation you have. So you will pretty much always go from a Z to a W, and almost never go from a W to a Z. I guess there's probably some theoretical or philosophical reason why you might want to go from a W to a Z, but most people would never do that. So you will pretty much always start with a Z, convert it to a W, and then interpolate in a W. So we're going to do the exact same thing here. So we're going to take these two values. I did not like that 100 value, so I'm going to switch that. It doesn't matter. It's just a different, I'm just going to set a different seed point. So this is going to be, actually, you know what? I should leave it as is, just because we want to see how different the interpolation is. I don't like that end state, whatever. What we're going to do is we're going to take these exact same Z vectors, and we're going to convert them to W vectors. And the way to do that is to iterate through all of your Z vectors, and you're going to run this command which says g.mapping. So remember, anywhere you see a uppercase G, that means the generator. So the generator has this mapping network that is sort of secondary to the forward pass. And what you do is you map your Z's to your W's. Another thing to notice here is that when you map to a W, you provided a truncation value immediately. So the W has sort of the truncation value built into it. So you won't be doing a truncation with your W. It's like little things you have to think about or like be aware of. Once we've got that, then we're going to get back our W values. So we'll convert our Z's into W's. So we'll just run this code here. And that ran, it didn't spit anything out because we're going to look at it in the next step. So a Z vector is always a single vector that is 512 dimensions. So you will often see that described as this, which is 1, 512. So this means there is one batch or one number, or one, you almost think about stacks, one stack that has 512 dimensions. A W vector often has multiple stacks. So that will be represented as something that looks like this, which could be 18 stacks of 512, or in this case, it'll be 14. It tends to be the case that the resolution of your model determines how many stacks you have in a W. A 1024 by 1024 model will always have 18. 256 by 256 usually has 14. I think 512 by 512 either has 16 or 18. And this is again settable in a config, but these are sort of the defaults that people usually use. So if we take a look at our first W vector and we print out its shape, this is called its shape. If we print this out, we should be able to see that it is 118, 512. Or sorry, 114, because we're at 256. So this is essentially saying there's one glom, or one thing that is 14 stacks or 14 channels by 512 dimensions inside of it. And we could also look at our second one, and that would be the same shape, right? So our W should always have the same shape, our Z should always have the same shape. Now, if we actually wanted to print out what that variable was, we could do this. We would just print out just the second W. And you're gonna see it's gonna spit out a vector. Now, I believe this represents, each one of these represents our stack. So there's probably 14 of these. Another thing you'll note is that they usually tend to be the same numbers. We'll talk about that when we get to projection. This is some other funkier stuff that we don't really need to worry about. But if you did want to look at what the actual numbers represent, this is how you would do that. So we'll want to do a linear interpolation using the exact same code. This is thankfully, because these are in a thing called NumPy, we can just run this exact same code and it will figure out how to do all the math. If you were to do this with JavaScript and you're used to arrays, you might know you have to go through every single array dimension multiple times. It's very annoying. It would probably take us forever to write that code for it. This just happens all at once, which is sort of the nice part about machine learning and especially Python and NumPy. So we can go ahead and just run this, and then what we'll do is we'll spit out the shape of the 121st dimension of this here. Actually, let me make this smaller again. Let's do 100 here, and then I'll reduce this to say the 50th vector. So our size is still 1 by 14 by 512. If we were to just say this, I believe, this won't work actually, sorry. What we could do is, could look at the length of frames W's. This is going to tell us to make sure that we generate 100 of these. Frame, not frames. So we have 100 of these, and then we can see that the 50th one is still the right dimension. You don't really need to do any of this. This is just here in case you want to look at it. Okay, and then now we've got our interpolation, and we're ready to look at all of how to basically generate this code, how to generate a video or generate each of these frames. So you'll find that generating images in the W space is slightly different, whereas before we used just the generator, right? We didn't say generator dot anything. We just said generator. Down here, we're going to use g.synthesis. And synthesis you can sort of think of as the W space. So G without anything is the Z space. G.mapping converts a Z to a W. And g.synthesis is the W space generator. So here again, what we're going to do is we're going to iterate through every one of those interpolations that is a W, and at each step we're going to generate the image, or what the model thinks of as the image. Then we're going to convert that to a value that is legible as an RGB, like Photoshop style RGB, so 0 to 256, and then we will actually convert it to an image in a PNG format, and then we'll save it into a folder that we're calling here output frames-w. So you'll see a lot of times this is just the same code repeated over and over with slight modifications depending on the generator. So if you were to dig into the generate code in my repo, you'll see I probably have turned this into a function, but you'll see it's pretty much everywhere in there. So we'll go ahead and run this. And that generated all of our images rather quickly. And if I come over here to refresh, output frames W, you'll see here are my 100 frames. And then we can go ahead and convert this to a video using ffmpeg again. And if I refresh again, you'll see I have lerp W. So let's go ahead and open both of these in QuickTime. So here is my W and here is my Z. Now, one thing I noticed almost immediately is that the W is actually a little different. For whatever reason, there's less color in here. I do find that sometimes when you convert a Z to a W, you get slight shifts. This is actually more prominent than I've really ever seen before. But if we were to play through this image, so let's play this is our Z space. So we'd expect this to be more entangled. So we play this. And then let's play the W and let's see if there's a difference. I don't know how easy that is to see over the streaming over Zoom, but I actually see a huge difference right around here. Right, so here we get this really gnarly, I don't even know what you would call this type of thing. Whereas here it's still gnarly-ish, but there's still a visible cat here. And this is the difference between entangled and less entangled, disentangled, is that here you get this like really messy sort of middle phase before it converts to this. Whereas here it feels a lot smoother, right? Like this image doesn't do this like weird sort of twisty thing. And we just get an image that looks pretty similar. But you will notice that our poles, right, like this end and this end look very similar. And so that's all the code underlying interpolations. So you can go ahead and play with. The one thing I want to note is some of you I know are really interested in easing or how to like change that linear interpolation. And what you'll find is if you Google like this stuff anywhere on the internet, like if you Google easing, you will often find, where's my lerp code here? You will often find that this code switches out. So if you want to do an easing method, actually, let's look this up. Python easing, I bet you will see that I have already looked at this page. Yep. Here we go. And then if we go into easing functions, easing. So you will see there is a thing that looks like this, right? And so this is quad ease in out. And so if I were to switch this to out.append, what you need to do here is I think it's instead of P? What is this? I think it's instead of T. Anyway, I've got this written somewhere, but basically if you can swap this in and out, this is how you change from a linear interpolation, which is this, right? So it's linear, meaning every step is the exact same increment, to a nonlinear, which is like an easing mode. You can easily swap in and out different interpolations. So actually inside of my code, if you go here, yeah, thanks Dusk. If you go here into generate, you actually see I've built in a bunch of easing methods that already exist. So here's line interpolate right here. You'll see I've got if linear, then you do this. If ease in out, then you do this. Okay, so this is what the code was. I just didn't have the multiplication correct. Bounce, ease in and out. So if you're interested in playing with sort of different interpolation or easing methods, you can look at how to change this value to be able to edit what you want to do. So I have started slowly building out interpolation methods into that script. But if you want to play around with them and sort of see how they work, that's the way to do it. Okay, so go for it.
I do have kind of a related question.
Yeah.
Because I've been thinking about like how you do walk in the like latent space, and like kind of, I don't know, one thing that often, I don't know if you're familiar with like noise, like Perlin noise or whatever, but often something that I'll do is I'll like kind of do a circular pattern to get like kind of smooth looping animations. But I don't know, I've been like trying to figure out how you would transfer like that to a super high dimensional space. Do you have any thoughts on that?
Yes, so I actually stole this code from Coding Train from Daniel. In here is some code that is noise loop. So this does that sort of noisy loop. What you end up doing, or like the hacky way to do this, is to actually do it on every single dimension singly. So if there's 512 dimensions, you actually do that loop. Like you basically run that across all 512 dimensions of the space. So that's what this code does. This uses open simplex noise to generate that noise value, and it is looping. I'd have to dig into code to remember how I did this, but it is something like you do use 2 or 3 dimensions of noise, so you do get that looping value. Yeah, so I actually stole that. Daniel Schiffman wrote some code to do that for Runway, and I just pulled it in here. So that's how we do it. There's probably a better way to do it using NumPy. Like there's probably some way to apply NumPy to like every single value, but this works, so I just left it in. Or there's other ways to do this using linear algebra, which blows my mind, and I don't even try to understand that. But that's another way to like. There's usually multiple ways to do this. Brute forcing it is fine. It's going to be slower, but it still works. So that's generally how I have done it in the past. So if you want to take a look at this noise loop function, that might help explain a little bit about what's going on there.
Yeah, great. Thanks.
Yeah, of course. Okay. I think we threw a lot at people, especially a lot of code. So why don't we take a 7-minute break? So we'll come back at 45 after, and then we'll look at feature vectors. So we'll see everyone in a couple of minutes. All right. Hey, everybody. So welcome back. So one thing I wanted to show, I should have done this earlier, but if all of that was really confusing and or you're just like, man, that sucked, I don't ever want to look at that much code again, I will point you to this notebook. So this is the sort of my like massive everything about this repo notebook. Let me drop this in the chat for everybody. Oh, I did already. So I just dropped it in here. So this notebook contains sort of every single thing I know you can do inside these models that I've written scripts for. So if you just want to generate, and honestly, like even if you, like this is how I generate most of my videos and interpolations. This line of code will do everything that I just showed you in those like 20 cells. So this will control how to do, so this is Z space, right? So we say space equals Z. You'll see we set some seed values here. We're setting our network and we're telling it how many frames to produce. This is the exact same function, or like the exact same thing that we just showed. And this is how to do it in W space. So this is probably easier for most people to use, and I would recommend that unless you're really interested in playing with the code. So this is what we just covered. There are multiple other types of interpolation methods that are listed here. There's a thing called SLRP, which should, in many ways, is probably better for Z space interpolations, but isn't necessarily better for W. I've explained a little bit more here. The noise loop, which Dusk and I were just discussing, is also here. And there's a thing called circular loop, which is ideally like less noisy than the noise loop. So this is all here. It's all documented. If anyone's interested in me explaining any of this more, like just DM me and I'm happy to either walk you through it or do some of that during the co-working session. So this will pretty much cover everything that we just discussed in the class as single line commands. So it will definitely it's a little bit easier to understand maybe, but maybe this also explains a little bit more about what you're doing here and is maybe helpful to understand. So we're going to cover next is actually down here is this thing called feature extraction with closed form factorization. One thing I want to note is that if you run this either now or after class, I have a sneaking suspicion it's going to break and I'll need to fix that. So give me an hour or two tonight to fix that. And this line of code will do the exact same thing that we're about to go through. This and this code here. So we'll talk about what this is, but if you are, again, sort of like, if your eyes glaze over when you see multiple lines of code that are hard to read, this is your solution. But I hope this will help explain a little about what's going on underneath the hood, so you can sort of understand it a little bit better. So again, I'm happy to walk through any of these steps. If people need demos or recordings of these things or want to talk about in a co-working session, just let me know and we can do that. Before I move on to feature vectors, any other questions about interpolations? All right, we will move on to feature vectors. So you might have heard me talk about feature vectors in a previous class before, but let's talk a little bit about what a feature vector is. So a feature vector is, let's say that like in an ideal world, what we really want to be able to do is take a model and say, I like this image, but instead of brown hair, I want red hair. Or instead of, I don't know, let's say for more of an abstract image, let's say instead of a majority of green, I want a majority of red, or I want to change the shape of the image. That's what we would describe as a feature vector. And if you're like me, when you first get into StyleGAN, you're like, oh, well, those 512 dimensions must be a feature vector, right? So if I take the first vector, vector 0 in that dimensional space, and I just interpolate between -1 and 1, that will do something that is readable to me, right? That will change someone's eye color, change someone's hair. And unfortunately, this is the challenge of how a machine thinks and how a human thinks. A machine doesn't really know what hair color is. It knows what pixels are, it knows what layers of the model do. And what you're going to find is that trying to manipulate a single dimension of that vector is just going to lead to like a bunch of globby stuff changing, and you won't really know what it is. So where the current research world is like people are trying to figure out ways to automatically generate and detect feature vectors. So we're going to look at a couple ways to do that today. But this is the challenge of it, is like we're actually going to, you can't just like take one vector in that dimensional space and move it up and down and have it be a human readable function. So here again, this idea that like, if I want to change a person's, hair length, but I also don't want to influence stuff like getting glasses. We also want to think about feature vectors as disentangled, right? How do I change someone's hair color without changing their lipstick color or without changing the background color? So feature vectors should also be disentangled. And what I think we'll find is that actually, in an ideal world, that's true, but in reality, that's not. There'll always be a little bit of entanglement in these things, but hopefully we'll find a little bit of change. And I also want to say, if you've played with any of the, I forget what they're called, I think they're called neural filters inside of Photoshop. Photoshop has started adding neural filters that allow you to age someone or change their hair color. That's this. That's essentially like, so Adobe worked with NVIDIA to take this model and figure out how to generate some of those feature vectors. So when you play with those, you'll even notice by aging someone, maybe their skin color changes, or even some of the hair color changes. So even those models are entangled. No one's really perfected a purely disentangled feature vector. But that's the future of this stuff is like, what if I could generate an image and then just by sliding some things, I can change things about individual features. That's the goal for a lot of these tools. So we'll look at a couple different ways to do feature vectors today. So what they used to do a couple years ago was they did a thing that was sort of a manual description of feature vectors. So let's say I wanted to figure out how to open someone's mouth. So a researcher would go in and generate like 1,000 images out of FFHQ, and they would tag them as like closed mouth, closed mouth, closed mouth, open mouth, open mouth, open mouth. And then they would look in the dimensional space, and using some math that is probably above me and maybe many of us in here, they would actually be able to generate like, what is the line of best fit, where at this end is closed mouth and at this end is open mouth. So there are sort of manual brute force ways to generate feature vectors. I don't think any of us want to do that. It's pretty time consuming, especially with non-facial things. It can be really, really hard to understand. So what people have started to do is like, what's a mathematic way to sort of generate these? So the first tool that I found that was sort of like really good at this was a thing called GAN space. What you'll see here is this is what they have done in this image is this is a person's face in here. And then what they use is they use a tool called PCA, which we'll talk about in a minute. Doesn't really matter. But anyway, they're generating two directions, right? So let's say this was our closed mouth, open mouth. This person in the middle kind of has a half open, half closed mouth. And actually you can kind of see it here, but this probably isn't the same. But like this is closed, this is open, right? So the idea is that a computer was able to look at all of the weights and variables inside of our model and sort of say, these are the most important variables or most important changes. And here's some examples of them, and you tell me what those mean. Again, because a machine doesn't know what these things mean. So it spits out sort of in order what it thinks the most important vectors are. So this first vector here, which is called C0, I hate using this description, but it's pretty obvious. This is converting a man to a woman, right? Like, or a male presenting to a female presenting person. So this is what the model decided was the first most important vector. Now, obviously, you're also getting entanglement here, right? You're getting a closed mouth and an open mouth. In an ideal world, you wouldn't get that. None of this stuff is ideal. The second vector here, C1, is the position of someone's face, right? So it's at this side, it is tilted one direction. At the other side, it's tilted this direction. So you can sort of like manipulate some of the direction someone's facing. And then this goes on and on and on. I believe in GAN space, there was maybe no limit to how many directions you could generate. This is what it looks like with one of my models. And again, it's much, much harder without faces, right? As humans, we are generated to like read faces very easily. It is a lot harder with non-facial things, but if you go through some of these vectors, you can see some things. So this vector, I think C0, is the direction of these flowers, right? This is pointing down, this is sort of neutral, and this is pointing to the right. But what's really interesting is when you get down into here, like look at C10. C10 is purple to orange flower color. And like if you actually look at this, I think I've got animations of these somewhere here, maybe even later in this demo. It looks pretty disentangled, right? Like the rest of the features generally stay the same. Now, when you actually animate it, there's a little bit of wobble here and there, but we're starting to get actually like good disentanglement. Oh, here we go. So this is the color vector. So there's a little bit of structural change, but overall the colors are pretty similar. So this uses a thing called PCA, which is Principal Component Analysis. I don't think anyone actually wants to discuss math in this class. So, and honestly, I kind of understand PCA from a theoretical standpoint. Basically what it does, it takes a bunch of the weights, or it takes a bunch of things in the dimensional space and compresses them to like the least dimensions possible while still maintaining the best representation of things. That's all it does. Again, for us, the important thing is that it gives us feature vectors. And so I've previously taught GAN space in a class before, probably about a year ago now. The problem with GAN space is that it works on a really old format of a non-official StyleGAN model, and it doesn't even use the current version of that fork to do stuff. So it's really out of date. It's also very slow. To generate feature vectors, it takes about a couple hours to run through your model because it's doing that PCA analysis. And then also there's lots of little stuff you have to tweak. I think, Nauko, were you maybe in that class? Maybe Adam was too, where we actually used GAN space and it was really annoying. It was like a pain in the ass to use. So I don't really recommend GAN space anymore. It was the precursor, was like the original thing to use. And it's definitely cool. You get these like really cool graphics that you can sort of like walk through and generate or like look at and try to figure out what's going on. But it was a total pain in the ass to use. So there's now this thing called closed form factorization, which a paper was released, I believe, in about a year ago now. And it said, hey, screw PCA, we're going to use eigenvectors. And I can't explain PCA, but I could not explain eigenvectors to you at all. But basically, it's the same idea. They're just going to use a different technique to generate feature vectors. And it also happens that closed form factorization, which is a mouthful, people just call it CFF. So yeah, it's always eigenvectors. Yeah, I know it's like the idea that it's the important vectors. That's the best way to think about it. So CFF is actually far, far faster. We're going to look at it in this class. It will take seconds to generate these. So like, thank God we don't have to wait around for this thing to generate a million files for us. So this is a really cool tool. We'll look at it in just a minute. but I'm really excited about how much easier this is in certain ways, and then it can be a little bit harder in other ways. Also, in setting up for this class last night, I realized that they updated this paper a couple months ago, and they've now built their own GUI tool and a collab to actually sort of visualize some of this stuff. So we might look at this next week. We might not. I didn't really get a chance to dig into it, but there are some GUIs that are starting to come up to, again, give us some features to like slide stuff. But as Dusk mentioned previously, even these GUI tools aren't responsive enough to really help. I find that if you close your eyes, move the slider and open them, you can kind of remember what it looked like before, but there's a little bit of a lag. So it's still not really that helpful. So we're going to look at how to generate a bunch of videos, and then we'll look at videos, and that'll help us understand what's going on. So these are some of the videos that we'll produce. So this is on a different model of mine, and this was, I believe, the index 0. So the idea here is that the lower the index, the more important the model thinks, or the more important this mathematic process thinks this image is, or these vectors are. But the challenge is that I find that like with the big vectors or the higher vectors, you get a lot more entanglement, and it can be hard to decipher what's going on. So in this case, I believe this might be the flower size vector. It's shrinking. So if you go left to right, it shrinks. But then you get this other side of thing, and I'm like, I don't know what that does. Index 3. So this one again feels like big flowers to little flowers in a more coherent way, but there's still some entanglement. And then we get down to index 5. I think this is a color change vector, kind of. So it goes from purple. There's like a little bit of entanglement, but not too much, to like yellow. And I guess it also kind of changes the type of flower, right? It's this like more scallopy flower to a more like single, like individual, I don't know what you call these, more smooth flower. So this is the challenge of any sort of these feature vector things, is that how you describe this is kind of like wishy-washy. The other challenge you'll find is that what we're going to do when we do this is we're going to set the middle value. So somewhere in here, when we do this, so we're going to set like this middle image. We're going to say, okay, slide my vector to the left, or like negate my vector, or add my vector. And what you'll find is that depending on what image you start with, your vector might do something very different. So we'll look at some examples of this, but it's kind of challenging to figure out how exactly these work. So I would say this is still a work in progress. We're still looking for tools to do this a little bit better, but I think it's fun to start seeing what you can do here, because you are starting to get to a place where you can control things a little bit more, right? So if you say, I know I want this image, but I want to go more purple flowers, well, you might say, okay, I can do that with index 5 and then negate it, right? And that brings me here. So like we're getting slowly to a place where we can do more control of things. And this is the challenge, or like the excitement of feature vectors, while it's still like a space in progress. So it's not really a perfect world where like, you could almost think about like, what if we could attach this to clip? Actually, that would be a cool idea. I don't know if we could do that. Anyway, I could think about that. But like, what if you could attach this to clip and then have clip say like, okay, orange flower to purple flower, and it would know which vector to look at, right? That would be the ideal world in the future, but that doesn't work today, or it could work, but someone smarter than me needs to help me get started on that. So this is CFF. This is what we'll look at today. And we'll look in this notebook. And again, just to highlight, if you want to do this in without looking at all the code, this one line will generate all your vectors. So what you'll do is you'll pass it your model, and then you will say, where do I want to save out these vectors? You'll save it as a PT file. So this will generate this, and this will generate it in a couple minutes at most. And then when you want to apply that, when you actually want to generate these images and videos, you'll use this apply factor. And then when you want to generate this across all of your feature vectors, and you want to spend 20 hours generating video that you will dump into like a terabyte worth of files into Google Drive, this line of code will do that. So I actually should record a video on this, and I probably will soon, but hopefully some of this will be described in the notebook here. So, but let's look at the code for this, just so it's a little like we can sort of understand what's going on underneath the hood. So once again, we'll just load in the official repo, and then we'll load in our cat model again. And then we will also load in all of our libraries. And then we will set our network pickle to be this file, right? So we want to do this. And a lot of this will start to look the same because we're just repeating stuff we've already done. So we're going to load in, we're going to say we're going to use a GPU, and then we're going to load in our model, and we're just going to load in the generator. Okay, so we've loaded in our model. So this is the code. Generate feature vectors. So this is literally the amount of code we need to do to actually do this. Now, here you will see eigenvector and this thing called SVD, which I believe stands for single value decomposition, which again, someone far, far smarter than me or someone really into math could tell you about. But this code will generate our feature vectors. And what we're going to do is we're going to generate our feature vector, and then we're going to save it out to a file, and we're going to call it cat vectors or cat feature vectors.pt. So I can kind of tell you what's going on in here. So this is basically going through every layer of our model. So remember that in the inside of our model is this deep layered model, right? So there's a bunch of layers, and each layer represents a different part of the image, or a different part of the structure of the image. So what it's going to do is it's going to go through those, and it's going to find the correct layers to weight, and then it's going to apply this eigenvector and this single value decomp thing to it. It does not matter, or at least today it doesn't matter if you know this or not, because I don't know this, so I'm going to assume we're fine. So we're going to run this code, and we'll find that it takes a minute at most. There we go, done. Like literally, that was all it took. It took less than a second. And if I refresh my folders here, we'll see I have cat feature vectors. Now we've also saved out this eigenvector. So this eigenvector contains all of our vectors. And if we just want to see how many it produced for us, we can run this. So this produced a shape of 512 stacks channels with 512 vectors. So the way to think about this is that there are 512 vectors, feature vectors, 512 feature vectors, and each of them manipulates our Z space, our 512 dimensional Z space with this math. So if we actually just want to look at one of these, so let's look at the very first index. And we'll just run this. So what is this saying? So what this is saying is that in order to manipulate our model along this vector, we would apply this mathematic value. Now, this is maybe confusing, but a really easy way to think about this is to compress it down to like one dimension, right? So let's say that we have a vector that sits at 0.5, right? You can almost imagine, like, let's imagine there's a 512 dimensional vector that sits at 0.5. Or we can think about this in 2 dimensions, right? So you've got a thing that starts at 0.5. And let's say at that position, we have an image that is a cat with brown fur. And this vector, we don't know for sure, but let's just assume maybe this vector converts brown cats to white cats. And what we want to do is we want to move our image in the least amount of entanglement possible to the white cat, right? So this is a brown cat and this is a white cat. And let's just say that the eigenvector says, well, the way to do that is to move this vector this much and move the other, or the x position this much, and the other vector this much. So that's all this is saying, is this is a direction, right? This is saying move this thing in this direction and something big will happen. So literally what we're going to do eventually is we're going to generate a z, and then we're going to add this eigenvector to it, and that will move us in the direction we want to move. So that's the process for this. That's how you apply a feature vector. This is just a crazy way to think about this is just, this is a direction. This is saying turn left or turn right. So maybe a way to think about this is like, if you're going down a street and you're just seeing a bunch of brown cats, and it says, if you want the white cats, turn right, That's what this vector is saying. It's saying turn right to get to white cats, or turn, distance is true too. Yeah, Grant's right. We'll look at distance in a second, but this is essentially the direction, and then it's sort of computed always to the value of 1, and then we can give it a distance score, which we'll do next to see how strong you should go. So yeah, distance and direction is good, but I think for now let's think about direction, and then we'll look at distance in a second. But yeah, this is essentially just a directional score to say, like, if you move this vector in this direction, you will get a different image. And the model has said, like, and I think there's something of value in that direction, which is the important part. Okay, so now we've got our vector, or all of our vectors are here in this value called eigenvect. And again, you'll hear me talk about index. Just think about index as the individual features, right? So if we come back to this, you'll see I have index 5, index 3, and index 0. So there are 512 of these. I don't, 512 might be arbitrary. I don't actually know. But essentially there's 512 vectors for us to look at, right? So the human process would be to give our poor little research assistant all 512 vectors and say, your job for the next month is to go through every one of these vectors with multiple images and tell me what each one does. So we can essentially label the vectors, right? And this is like, so again, when we go back to those neural filters in Photoshop, that's what they did. Someone went through all those vectors and said, this vector changes hair color. This vector changes lipstick color. This vector changes age. And sometimes you'll find that you're a vector where you're like, I don't know what this thing does. So who knows? We'll just toss it out. But that's essentially the process. So here's how we're going to make some of these images. So what we're going to do is, this is code just to generate, this to display our images in Colab. So we're just going to run this function just to save it. And now we're going to take that same cat, our seed 20 cat, which is our mascot for today. And we're going to, again, generate our z value. So we're going to take this exact same seed value. We should get the exact same cat out of it. And we're going to generate an image of that cat. So we should see our same cat from before. This is always the slowest part of this. Cool, and there's our cat. So this is the cat we've seen before. So now what we want to do is we want to take this cat and we're going to move it along a vector. So what is going on here? So seed equals 20. Okay, oops, 20. So we're going to take our cat and we're going to do the exact same thing we did before, which is like save that variable into NumPy, and then we're going to take our vector index, right? So we could take any, this could be any number between 0 and 511, because it's a total of 512. So this could be any number. So why don't we start with 0, just because that'll be our big number, essentially, or like the one we think will have the most change. And then we've got a thing called degree, which, as Grant mentioned in the chat, you could sort of think about this as distance, or I would think of it as strength, right? How strong do we want to change the vector? So what you'll often see is people do between 0 and 10. 1 is sort of the default. If you apply 0, you will basically say, like, don't apply anything to that number, right? So again, if we think about our numbers as we had 0.5, 0.5, and then the feature vector was like negative 0.1 and negative or 0.1. If you multiply this value times 0, you're going to get 0. So you won't get any change. So your value here should be some increment. And most people usually do like between 7 and 10. If you make this too high, you will get some noisy, colorful mess because you've pushed the vector too far, right? So you can think about this as like, again, remember that the vector, the latent space in StyleGAN is -1 to 1. So if this value is like 0.01, but you multiply this times, I don't know, 1,000, you will get something outside of -1 and 1, and you'll just get some noisy blobby mess. So usually people want to set this, like I usually set it to about 10. You can play with this value depending on your model, but I would say between 5 and 10 is usually a good distance and or strength. But it's also often called degrees in these papers. So you've got degree, distance, and strength, and these all sort of mean the same thing. So we're going to use the 0th, the first vector. And then we're just going to say for the current vector we want to use is eigvect of 0. So this is the same thing. So we're just saying grab that first vector. And then the direction is degree, which is strength, times this vector, right? So we're actually going to multiply this value, whatever that vector is in there, times a certain strength or distance or degree. So what this code is going to do is we're actually going to generate 3 images. We're going to generate an image on the left, which will be the negative distance. And in the middle, we'll generate our image. So this will be our C20 cat. And then on the right, we will have our positive direction. And it's always good to think about these in positive and negative directions because it can sometimes help you understand, if I go in the negative direction, I get this. If I go in the positive direction, I get this. And sometimes you'll see something that goes across both, right? So that could be size. It could be other things. So we'll look at this as we go through this. So we're going to take these vectors. We're then going to generate an image for each one of these vectors. So this is, you'll have seen this code before, right? This is our pass it through the generator, convert it to a RGB image that we can understand. And then we're going to skip saving it, but we'll just show it in Colab below. This torch.cat just says to combine these 3 vectors into one file so that we can pass that whole vector in here. It saves us milliseconds, but it's kind of nice to batch these things up. So let's go ahead and run this and take a look at it. Okay, so here in the middle, we have our one cat. And here on the left, we have what the negative direction did. And here on the right, we have a positive direction. What do you like? How would you describe this? Well, this one's a little bit more yellow. This one's a little bit more front facing, I guess. So it's kind of hard to say. Sometimes you have to change the seed value. So let's try a different seed value. And okay, now I've got a blobby cat in the middle. I've got, I don't know, a different cat on the right. And this is a challenge. So I would generally say like 0 is going to have the most massive amount of change. And it can sometimes be really hard to tell. So I might choose something a little bit lower. I believe I had good results with 3. Let's try this one. So this code will help you sort of like iteratively sort of generate different images and sort of see what you've got here. So what you want to change is you want to change the seed, the vector, and maybe the degree or strength. Okay, so now I've got a different cat here. I wonder what vector did I have before that looked really good? Okay, so this one's kind of interesting. The 10th vector looks like it maybe does the position X, Y, or like this one's a little bit higher, this one's a little bit lower, and does color. So you might want to also change this, like let's try a different seed and let's see if we get sort of the same sort of effect. Okay, didn't really get that. So this is one of the challenges with feature vectors is like you kind of almost want to generate a grid that looks more like this just to be able to sort of see the differences between things. So maybe that can be some good homework examples of how to do that. Another thing you might want to do is this code below here. This code will generate, instead of 3 values, it will generate 5. So this might help you understand strength a little bit more to see if maybe 10 is too strong, right? Maybe strength 10 here is like always leading to this blobbiness. And maybe what I want to do is I actually want to do a little bit lower strength. So let's run this code and I'll explain what's going on here. So this is using my exact same seed value, right? It's using the seed value from up here because it's not being set anywhere in here. And then what we're doing instead is we're getting, I guess it would be degree 5 and degree 10 in the negative direction and degree 5 and degree 10 in the positive direction. So if we come back up here and we do, let's do, go back to seed 20, and then we'll run this cell. So this, and again, I changed my vector index. So I should do, this is 10 here. So let's do 10 down here as well. So here again, we'll sort of see how this changes. And I do think there's something, you can almost see this animating, right? It's sort of like moving down and it's changing color. So we could try like a really deep, let's try something a little bit deeper. Let's go to 100 and let's try that. So what I've tend to notice is that the lower vectors, the larger you get, which is technically lower in change, can sometimes be a little bit easier to understand because there's less entanglement often. So in this case, it looks like it's sort of head size and maybe head tilt, right? So in the positive direction, it makes the head bigger and maybe like straightens it. And to the left, it makes the head smaller and does this. Now we could try this again. Let's try this with, I'm just going to grab my seed code here. And let me drop this in here. Let's try this with a different image and see if we get a similar result. Let's try seed 0. Okay, so this actually does make sense, I think. This is the head scale vector, at least for 2 images, right? So this head is getting larger and it's kind of rotating as well. This head is getting smaller and maybe kind of rotating as well. Let's try one more image and see if that plays out again the same. Okay, didn't really work out there. So again, this is one of the challenges with feature vectors is that you will get slightly different results depending on your input. And you might have to dump out, maybe what we would actually want to do is run this code almost iteratively across a number of seeds and spit out a bunch of these that stack to see if we get different stacked images that all look the same. This is a very creepy looking cat. This cat has somehow managed to go from 1 cat to 2 cats to a merged cat. So I don't know, maybe that's its own, maybe there's something to do with the vector in there. So this is the very annoying part with feature vectors, and especially the annoying part when you aren't dealing with faces, right? Because faces are a little bit easier for humans to understand. There's also far less that could change in them. I will also say that it's very likely this cat model has been trained on a much smaller data set than FFHQ, and the less data you have in your model, the more noisy your model will be. So you've got like sort of a endless string of problems here, but I still think this is very fun. This is a really I could probably spend, if someone let me, I could spend days doing this to just sort of explore what I get out of things. So this is a fun way to play with things, but it can be really challenging and really time consuming. So the code over here in this notebook, instead of applying that factor as a string of images, it will actually apply it as a video. So if you stick -- video to the end of this command, and you say, okay, so this is literally what it says. It says, take the first vector with a degree or a strength of 10 and apply it to these seeds. So in this case, I did 0, 1, and 20, and apply it to this model using these feature vectors and dump these out into a video. So this will generate videos of these 3 seeds with this, pretty much a video of this video, an interpolation video that does this. So you may find that videos are easier. Another nice thing is that if you save this directly to your drive, to your Google Drive folder, you could let this run for a couple hours, walk away, go do something else, and come back and have a bunch of videos to watch. And you could begin to maybe sort of decide like, hey, this looks really cool. Like maybe what you really want to do is do 0 to 20, which will generate 21 seed values and generate 21 videos that you can then watch and sort of compare. Like, okay, the 0th vector does this. The first vector does this across all of these. So this is how you would do it manually on a single eigenvector or a single feature vector. If you want to run this on all 512 vectors, you run this line of code. So this will take every one of our 512 vectors and it will apply that video code creation to every one of them. So you may want to do 0, 1, 20. So this will generate 20 videos at 512 vectors. And you will definitely want to save this to your drive because if you don't save this to drive, it will probably crash your Colab depending on how much space you have. I will also say this will generate a lot of video with high-res video and a lot of them. So make sure you have enough space in your drive account to do this. This is probably overkill, but if you just want to batch it and then this code, I believe, takes about 20 hours to run. So it takes about the time of a Collab Pro session. So if you want to run this, you can like run it and then like the next day look at it. That's probably one thing you do. I have run this on a couple of my models and never looked at. It's like how many videos of these can you watch at one time before your brain just melts? It's probably not 512 times 3, but maybe there's other ways to do this. Maybe for those of you that are coders, maybe what we want to do is actually generate a grid, right? Maybe we want to take this, and actually this might be something that I try to do in the future, and actually just generate a grid of these stacked, right? So take 10 of these and stack them. And then maybe at a glance, you can see like, okay, across all these, what's the same or what's different? That may be a better way to visualize this than video. But I do find video helpful because it sort of shows you how things animate, because sometimes you don't really see how they animate from 5 images. Like I don't really want to know what's going on here. I'm going to save this though. This looks fun. This will be a good Twitter image for all the people who have not yet unfollowed me. Yeah, you could probably do an ffmpeg one-liner. You could definitely stack them. Actually, that should be my ffmpeg class. I know a couple of you are in that class. That'll be our ffmpeg class homework. How to stack all these videos together to play. We could do that very easily with a VStack. So that's it for this class for today. So your homework for this week is, first off, just generate some videos. It's fun. It's easy to do. Generate some interpolations either in W or in Z. I definitely recommend doing both W and Z and seeing how they differ and seeing what you like more. So use the same seed values, the same length, and generate them in both Z space and W space and see how they differ. A nice trick, because they won't always be labeled, is the W space video files will always be smaller than the Z files because of how video compression works. The W will always have less change in them, so therefore the video files will be smaller. So that's a nice trick to tell if you ever are confused about which one is which. Also, if you're interested in maybe what Dusk was talking about, either doing randomization or noise, or maybe even doing easing, maybe take a look at how you could do that. And then feature vectors. I would say generate a bunch of feature vectors. Maybe don't do all 512 of your model, but I would say do the first 50, do the first 20, and see if there's anything that does look like it is a feature vector. In the future, especially when we get into like audio reactive, we might look at actually using that feature vector as an input to our audio reaction, right? So maybe we actually want to say, hey, when a bass noise hits, move the feature vector. So, change the color of the image by bass or by snare or by something. So we might actually use those feature vectors in future classes. So I would definitely recommend playing with this. I also think this is like the future of machine learning image making is this. Having most of us are kind of cool with the sort of open-ended space of machine learning, but like for a designer or an artist, like what you want is control. And this is the eventual future of controlling our images in better ways. So I think you'll find that there's some interesting opportunities here to play with. I know Dusk is really interested in making GUIs. This is probably like a very cool GUI that eventually GPUs will be fast enough to just generate. Like I tend to find that if you have a 256 by 256 model, you might actually be able to get not real time, but like much more responsive sort of data. So you might want to play with that and sort of see. Yeah, so that's it. So next week we're going to look at, I might look at the feature vector GUI tool that is in that CFF notebook. I'm going to play with it this weekend and sort of see if there's anything cool there. We might look at that. We will definitely look at projection next week. I know I've covered projection in previous classes before, but there's lots of new things that we can do with that. We'll also look at how to animate between projections, which I think is also fun. So we'll cover a lot of that next week. And if that isn't a full class, I will find more things to jam the class full of, more fun stuff to work on. So yeah, any questions?
Derek, have you found with less diverse data sets, maybe is it easier to recognize features, or is it actually more challenging because the images may be more similar?
It probably depends on the data set itself, right? Like again, FFHQ is nice because all of the data is aligned really well. So like, if you were to use like that FFHQ wild, you might be changing a vector and all it's doing is changing the position of someone's head. And like that's really hard to track across multiple image data sets. So it's like almost like, is your data set aligned? Is it more similar even after alignment? Then yes, it probably is. And then two, are our brains even like cognitively built to notice changes in features, right? Like that's what's so nice about faces, even though I don't like to do as much face stuff in these classes, because I think it's fun to explore things beyond faces. In something like this, it's really easy to tell like, oh, someone's eye color changed because our brains are wired to notice those things. So with like animals, people, like we can notice these things. With stuff like abstractions or flowers that are really noisy of a data set, or I've run this on wiki art. And again, it's even with wiki art, it's like so hard to tell the difference because it's trained on so many different things that one thing might be changing from a person to a place. Like that might be a vector, is it actually goes from a person to a place. Another one might be going like, I'm gonna make mountains taller while also making trees smaller. It's like it's really confusing. Um, I think the other challenge with this is that because we're limiting ourselves to 512 dimensions in most StyleGAN models, um, you know, if you were to increase that exponentially to say 1024 or 2000, there might be more features within a bigger model. We also have to then traverse that many more pieces, right? So it's like I mean, I wasn't really joking when I said I think CLIP might actually eventually be a tool you bolt on top of this so that you can build feature vectors. Then you run each one of those through CLIP, and CLIP says, here's what changed. Or a CLIP-like model says, here's what changed as a language. And you can say, like, oh, cool, this vector is now this, or this vector is now this. And then it's actually controllable, right? I would not be surprised if in a year or two, that's what we have. Someone is taking a feature vector, running all those features through CLIP or like a fast version of CLIP, getting back text-based descriptions of what changes, and then we've actually got sliders that can say, here's what this thing does. So all this to say is like, this is going to be a really fun world to be in for the next couple of years. And like, who knows where we're going to end up, but I think there's you will probably find your individual model behaves very differently than my individual model because of training and other things. So it's kind of all over the place. Sorry, that was a long way to get to that description, but like, it's going to matter depending on a lot of different stuff.
Just one quick question. When you were doing the feature vector manipulation, were we working in Z space or W space?
Yeah, that's a great question. So I was working in Z space or Z space for you Canadians. But I did actually show an example later on that I didn't get to here that does take these endpoints and then bring them into W space. So this code here actually brings them into W space and interpolates them there. Like if we actually just run this in W, crap, 1 second. So we want W space. You'll see that the W space is a little bit cleaner. The challenge here is that we've actually removed that middle point, which is where we started from. So we'd probably have to think about like, what do we want to do W space? Like these are the 3 points, and then we go W from here to here and W from here to here. That might remove some of the entanglement. That's my theory, is that would remove a little bit of entanglement, but you would still get these 2 poles. So if you were to look at this, like the 3-point model, you would basically get these 3 points, and it might remove some noisiness between those. So that's something to look at, is like, how different is a W space interpolation between these 3 points versus a Z space?
Thanks a lot.
Yeah. Other questions? One more thing is I will say in here, this link, let me just drop this in our chat so I have it for our notes. This link opens the Colab notebook for CIFA, which I guess that's what they've renamed CFF to. This will show you some predefined vectors for a couple different models. So there's an anime faces, there's a car, there's cats, there's Celeb HQ, and then there's bedrooms. So if you want to play with this is sort of the Colab GUI. As I said, I find it's not fast enough still. It's still a little bit janky, and you can't really see stuff animate, so it's a little bit hard to use. Another thing that they're doing is I think they're maybe changing stuff by layer within the deep layers, which is another way of looking at this. So this code is based on a paper that they wrote in July of last year, and they updated it 9 months later. So they might have found some new ways to manipulate this. So again, I'm going to look at this and see if there's updates to this. But you might want to play with this and just sort of see, what does a Colab GUI look like? And is it fast enough for me to actually like feel like I understand what's going on? I personally found that it wasn't, but you might want to play with it and see what you think. Any other questions? All right, so we have co-working sessions Saturday afternoon and Monday. So if you are interested in learning any of this, or even if you just have questions about a project you're working on, like I know Alicia and I were talking about a project she's working on, and maybe I was giving her tips on, the right tool to use, the right model place to save it, that sort of thing. So even if you have questions like that, like it doesn't have to be directly related to this work we're doing week to week. So please feel free to jump in those co-working sessions and ask questions if you have any. All right.
I did think of one question.
Please.
So last week it seemed like CLIP mostly was like about generating images from descriptions. How do you go about it? It sounds like it goes the other way too, where it's like you can generate a description from an image. How do you go about that?
I have a notebook that I can do that. Let me ask Ryan. It's technically closed. It's not closed source, but it's technically like in private beta because there's some racism inside of Clip, so he doesn't want to make it like too widely available. Let me ask him if he's okay with me sharing it with this group. If he is, I'll share it with folks. You can get it off his Patreon if you want to send him $5. But that's probably the best way to do it today. He said he's going to make it public at some point, but he's just sort of like slowly opening it to researchers to see if it's like really too bad. So let me ask him and see if I can do that. That would be one tool to use. One thing I will say about that is it requires an iterative process. So it's my future vision of like take a feature vector, dump it into Clip, and then in seconds you've got an answer. Wouldn't really work for this. You would actually have to do and Grant, maybe you could think about how to do this, or maybe we could take it to the Discord, is like, how would you take what you see in distance -10 and what Clip sees in +10 and like subtract those two and say, here's the difference. Also, that just takes like, I believe about 30 minutes to an hour to really generate good values. So it would not be a like immediate process. But I would say in 2 years, Clip will be much faster and we'll have all these tools at our fingertips.
Well,
yeah.
Also one thing that's interesting is like in GPT-3, you can like subtract certain things from other things and it'll give you that. But I haven't played around with GPT-3 much. So
you can do that with.
Sorry, go ahead.
You can do that with vectors in Clip too, because it takes the strings, the text strings, and then embeds them into a space, and then you can do arithmetic on those vectors too. So you can subtract the color red from a string, for instance, and get an entirely and it works. And you can add two together, and it works frighteningly well.
Yeah, so it's definitely possible within Clip to do that as well, to say subtract this image or the description of this image from this image and what's left. So yeah, I think there's lots of opportunities.
And the text too. You can also add a text embedding to images embedding. And Ryan was playing around with that. He was adding a man with sunglasses to a picture of himself, and he got an image that depicted himself with sunglasses. It was eerie.
Yeah, so I mean, there's probably lots of opportunities to do this. Maybe the future of this sort of feature vector stuff is actually just using Clip and just saying, hey, take Clip from like take this image and make it older, make the person older, and Clip will like do the loss scoring and move stuff around that way, and then you've got a vector that way. So maybe all this eigenvector bullshit won't be the future. It will just use Clip and that'll do everything for us. So yeah, I think there's lots of opportunities, and just about finding the right person who knows machine learning a lot better than me to maybe start us on that path. So yeah.
I just thought like with Clip, can you also get like I know that there are some models to get like the latent space of a real image. Can you get that out of Clip also, or what? Have you tried that?
Yeah, you can. So we'll look at projection more next week, which is essentially that. It's taking a real image and projecting it into our model and finding the closest representation in our model. So that's definitely a possibility. Clip can do that too. So I know Adam was interested in looking at this. There's a model called, or there's a tool called StyleCLIP, which attaches clip to a StyleGAN model, and then you can use stuff like say like, hey, like make this image more brown, and it will figure out how to do that. And all these the things underlying all these things, as Grant mentioned, almost all these models have some form of latent space. So Clip has a latent space where there are instead of here's a placeholder for an image, it's here's a placeholder for a word or a phrase. And you can do math between those, right? Just like you can interpolate between these, you could essentially say like, what are all the words between brown and blue? And like go through that latent space and give me all the words you see. Now that doesn't exactly work in a language model because language models are discrete, but that's like kind of beside the point. But you could essentially do that. Yeah, there's a lot of like, yeah, embedding is the way to think about it. But yeah, it's there's lots of tools, and I believe the future is there will be more tools, and there will be smarter tools, and there'll be faster tools for all these things. And like understanding sort of how they work beneath the surface means that when a new model comes out, you can quickly jump on it and find all the tricks, and then be able to apply these things to that. But yeah, I think Adam requested we look at StyleCLIP, so I'm gonna dig into it, and maybe toward the end of class we will actually look at StyleCLIP to look at how to do that. My guess is that StyleCLIP came out pretty much right around when Clip came out, and the people who have done all these image generation clip tools have found way better techniques to sort of optimize. So I think Adam was saying that StyleCLIP kind of felt kind of mushy and didn't really do what he wanted it to. My guess is that there are new techniques to actually make that happen, and I'll just have to dig around and see who's got them. But yeah, I think there's lots of opportunities for these tools to get better and improve. All right, if there's no more questions, we will wrap it up for the night. So again, please make some stuff this weekend and just drop them in the Slack channel. For those of us in the US, it's probably a 3-day weekend for you, so maybe you got a little bit of extra time, or maybe you're just going to leave the house. Either of those sound great. But if you do have extra time, or if you just make something cool, drop it in the Slack. If you make more creepy cats like me, please drop creepy cats in the Slack channel. Maybe if they're super creepy, maybe like stick them in a thread. That way you don't creep out people too much. All right, everybody. So I'll see you in a co-working session, and if not, next week. Bye, everybody.